Hey, welcome to the Explainer. Today, we are going to dive into one of the most powerful tools in any RF engineer's toolkit, the Vector Network Analyzer. We're going to figure out how this incredible device takes the totally invisible world of RF reflections and makes it crystal clear. Now, before we really jump in, just a quick heads up. This is part 10 of a big 20-part series. It's all based on a super detailed report on radio frequency propagation from the RFI detectives who are part of Virtualization Options, LLC. So yeah, if you're an RF tech or engineer, you are absolutely in the right place. So here's the game plan for today. We're going to start with the core RF challenge, then see how we make the invisible visible. After that, we'll get into the language of reflection, talk about the path to precision, and finally, bring it all home with how we go from data to design. Let's get into it. Okay, so let's start with a really fundamental question. One that I'm sure every RF tech and engineer has asked themselves 1,000 times. You've got all this power coming from your transmitter, but why isn't all of it actually getting to your antenna? I mean, where does it go? The answer is, well, it's complicated, but we're going to figure it out. And that question brings us right to our first big topic, the core RF challenge. We're talking about an invisible enemy, and its name is impedance mismatch. This is the thing that's quietly stealing your power and wrecking your system's performance. So what is this thing? Well, in pretty much any circuit, you only get the most bang for your buck, the maximum power transfer, when the impedance of the source perfectly matches the impedance of the load. But when they don't line up, power that should be going forward literally hits a wall and bounces backward, right back at the source. It's just wasted energy, and it can cause a whole mess of problems. And you can really see the difference here. Look at the left, a perfectly matched system. Think of it like a perfectly smooth highway. All the power, all the energy just flows right from the source to the load, no problem. But on the right, that mismatch, it's like a traffic jam, or maybe a better analogy is a dam in a river. The energy hits it, and a huge chunk of it gets bounced right back, leading to serious signal loss. Okay, so how in the world do you fight an enemy you can't even see? Right? We need some kind of special goggles, a way to make this invisible problem visible, so we can measure it and actually understand it. And that, my friends, is where our hero instrument comes into play. And here it is, the Vector Network Analyzer, or VNA for short. The best way to think about it is like a superpowered, genius-level ohmmeter for the RF world. See, it doesn't just measure a simple value like resistance, it's measuring complex impedance, and it does that by looking at two things. The magnitude, which is basically how much signal gets reflected, and the phase, which is all about the timing of that reflection. That's the vector part, and it's key. So what is this thing actually measuring? Well, first off, as we said, the magnitude of the reflected signal, how much of it is coming back. Then the phase of that signal, what's its timing? This information gets packaged up into something called S parameters, and we'll talk more about those in a sec. And the coolest part? It doesn't just do this for one frequency. It sweeps across a whole range, giving you a complete picture of how your component behaves. All right, to really get the most out of a VNA, you've got to learn how to speak its language. And that language is all about S parameters and a really cool tool called the Smith chart. So let's decode it. So S parameters, you'll also hear them called scattering parameters, are basically the universal language for describing how a network behaves at RF frequencies. Think about it. When an RF signal hits a component, it can do a couple of things. It can bounce off or scatter back where it came from, or it can pass through. S parameters just give us a precise way to measure all that bouncing and passing. Now, for the specific problem we've been talking about, impedance mismatch, we are going to be laser focused on one particular S parameter, S11. You can also call it the reflection coefficient or return loss. It's super simple. It tells you what proportion of the signal you put into port 1 gets reflected right back out of port 1. And the goal is simple too. You want that S11 value to be as low as possible. A low S11 means a great match. Okay, but here's the tricky part. S11 isn't just one number. Remember, it's a vector. It's got both magnitude and phase. And it changes depending on the frequency you're testing. So, how in the world do you plot all of that information in a way that actually makes sense? Well, you use this absolutely brilliant tool, the Smith chart. This is without a doubt the native language of the VNA. It's this special kind of polar plot that was designed for one purpose, to graph the complex reflection coefficient. Every single possible impedance you can imagine, whether it's resistive, capacitive, or inductive, has its own unique home on this chart. And right in the dead center, that's the bullseye. That's a perfect 50-ohm match. So this is great. We've got our map, the Smith chart, but before we can actually trust that map to guide us, we have to make sure it's dead on accurate. And because a VNA is such a ridiculously sensitive instrument, we have to be super careful and account for everything in our test setup. And that leads to a really critical question, right? Think about it. The signal from the VNA has to travel through your test cables and connectors just to get to the thing you want to measure. And those cables, they add their own delays and losses. If we're not careful, we'll end up measuring the cable itself instead of the actual device we care about. So how do we fix that? The answer is a critical ritual, a 3-step process called an open short load calibration, or OSL for short. It's pretty straightforward. You take 3 known standards. First, you measure with the cable end just open. Then, you measure with it short-circuited. And finally, you measure it with a super precise 50-ohm load. By doing this, you're essentially teaching the VNA what your test setup looks like, so it can completely ignore it and focus only on what comes after. What this whole calibration ritual actually does is it establishes something called a reference plane. This is the exact physical spot where the measurement begins. It basically moves the VNA's point of view from inside its own box all the way down the cable to the very end of your connector. This is how you make absolutely sure you're measuring your device under test and nothing but your device under test. Okay, now for the fun part, the payoff. We have our accurate, perfectly calibrated tool. We can speak its language. So let's put this thing to work and finally solve that impedance mismatch problem that we started with. And here you go. This is what it looks like in action. The VNA just sweeps across all the frequencies you care about, and it draws this trace on the Smith chart. You can instantly see exactly how the impedance is behaving. If you're looking at an antenna, for example, the spot where that trace gets closest to the center of the chart, that's your money spot. That's the resonant frequency, where you have the best possible match. And this, right here, is the whole point. This isn't just a pretty graph. It's a roadmap to a solution. The Smith chart doesn't just point out the problem, it literally tells you how to fix it. Depending on where your impedance point is on the chart, it tells you exactly what you need to do. Add a little bit of inductance here, a little capacitance there, to physically move that point right into the bullseye in the center. It's incredible. So that's the real magic of the VNA. It takes RF design out of the realm of guesswork and, messy calculations and turns it into this precise, visual, almost intuitive science. It takes that invisible enemy, that reflection, and puts it right in front of your eyes, giving you all the power you need to design the perfect match.